Welcome to the next lecture from our student seminar. Today, I have a pleasure to welcome Atabak from the Czech Academy of Sciences, who will give lecture on ghosts, whether classical, what does it mean, does it have good meaning in classical mechanics, and then on his research on quantum ghosts.
Thank you. All right, that's the first introduction I've gotten. So, yeah, as you were told, I will talk about ghosts today. So the aim of today's talk is to, in a relaxed way, give you guys an overview of what ghosts are in theoretical physics, their relevance in theoretical physics, some of the problems they can cause in dynamical theories, especially when they're dynamical, and then I will present you with some recent work on theories that contain ghosts, classical theories, classical mechanical theories that contain ghosts, that are actually stable. So they don't suffer from any sort of pathologies, even though their Hamiltonians are unbounded from below. And then that will lead me on to my work right now, which is quantizing such a system. And I will talk to you a little bit about what we've done, and I will show you some animations, which I think look quite nice. And then, yeah, and then I'll summarize and we'll be done. So let's start off with an outline here. As I said, we'll start with talking about what ghosts are. We'll talk about their problems. I'll give you some examples, and I will present you with a theorem known as the Ostrogradsky theorem. And this theorem is, okay, you should take it with a pinch of salt because it's a bit specific and there are a lot of ways to circumvent it and a lot of exceptions. But generally, it holds true for most of our successful theories in physics today. And I will show you a couple of worked examples on the blackboard. And then, as I said, globally stable ghosts, quantization, and then I'll conclude. So let's start off with asking what ghosts actually are. So let's take a look at this sort of toy model standard Hamiltonian. And you can see that, okay, this guy, if we assume that the potential is positive definite, this guy is bounded from below. And essentially, if you pick this is going to be conserved, right? So if you pick a starting value for the Hamiltonian, there will be an interplay between the kinetic term and the potential term such that motion in phase space will be bounded, right? And this is important because, so this is in a field theory setting. It would look something like this, right? For a classical scalar field in the correct signature. So a ghost is a particle, a dynamical degree of freedom that has an improper kinetic term. And there are ways of defining that, but the point is that they unbound the Hamiltonian from below and make it non-definite. So all of a sudden, you have negative energies accessible to your dynamical system. But not only that, if your degree of freedom can interact, now, let's say we pick a constant value for this ghost Hamiltonian, right? This value will be conserved during time evolution. But the problem now is that you can have infinite negative contributions from this term and infinite positive contributions from this term, keeping age constant, meaning you can have something called a runaway, right? So essentially, you now have unbounded motion in phase space. And what this corresponds to is essentially that the volume in phase space, which is dynamically accessible by your degree of freedom, is now infinite, whereas in the healthy case, it's finite. Okay, so why do we talk about ghosts? Why would we even consider a theory where you have a dynamical degree of freedom that makes your Hamiltonian non-definite? So, okay, don't ask me about the details, but in quantum field theory, they're necessary for handling our gauge redundancies, essentially. So, but they're introduced in a way such that they're non-physical, and they just amount to helping us count the paths in our path integral. However, in modified gravity, these guys show up all the time. And as to why we want to work with modified gravity, well, it's because GR, albeit very good, it's not perfect, right? And we have more and more observations pointing towards the fact that GR is not our final theory of gravity. So then we need to look beyond that. And then there is this theorem called Lovelock's theorem, which essentially defines how GR is unique. And if you want to go beyond GR, you need to break this theorem, right? And one of the ways of doing so is by introducing new fields into your dynamics, right? Many times, these fields become ghosts. So, let's see if this, okay, some examples, right? So generally, f of r scalar tensor theories will contain ghosts. There are papers that show this. Generally, if you have a higher derivative theory, you can introduce auxiliary fields, and some of them may turn out to be ghosts. Generally, this is a possibility. And for instance, if you, I mean, many years ago, when people were trying to give some mass to the graviton, essentially what they did was they took the GR action, they linearized it, and they introduced a mass term. But then when they did that, instead of propagating 2 degrees of freedom, the theory now propagated 5, one of which was a ghost. Also, there are some new possibilities in cosmology. Essentially, we have some observations today. Recently, there was a paper that came out from the DESI measurements, which essentially hints, or at least suggests, that there is a possibility that the cosmological constant changes in time, right? And this would correspond to an equation of state parameter that is less than -1. And one way of modeling such a universe would be to introduce a field, a scalar field, but with the wrong kinetic term, aka a ghost. So there is a lot of relevance for ghosts in theoretical physics, especially modified gravity and cosmology. So, and especially since we, unfortunately, many times have to deal with them even though we don't want them, it's relevant to try to understand what they actually entail. Okay, so what are some of the problems with ghosts then, right? As I said, the Hamiltonian becomes unbounded from below. So now you have negative energies that are accessible. Okay, if the ghost is dynamical and interacting, that's also a problem because now your system, as I said, might experience these so-called runaways, right? Where your dynamical degrees of freedom might run off to infinity, but because you have negative contributions to the Hamiltonian, they will cancel out and you will keep the Hamiltonian constant. Furthermore, your vacuum state is not well defined anymore. I mean, we don't have a lower limit to the energies of our system, right? So if you place, I don't know, if you have a classical potential that's a saddle, and you place a marble in the middle, that guy's just going to roll down. There's nothing preventing it from doing so. In a classical field theory, if you have the vacuum in the sense of a lowest energy, just constant scalar field, you will see just excitations of positive and negative energy modes appearing and canceling each other out to, essentially keep everything constant, but nonetheless you have runaways. So, yes. And because of removing the lower bound, quantization also becomes a bit ambiguous because, okay, what's our vacuum state? And especially if in terms of ladder operators, you could have a vacuum, you could have 2 vacua, right? You could have a vacuum where you annihilate a positive state or that you create a negative state, both of which would define a vacuum in a sense. And this would then eventually lead to negative norms. One can show that, but I will not go into detail. Okay, so we've talked a bit about the problems with ghosts. They generally introduce instabilities. There's the possibility of runaways, and quite frankly, negative energies is quite unphysical. So there's this theorem that's called Ostrogradsky's theorem. And essentially what it tells us is, if you have a Lagrangian that contains higher order derivatives, and it's non-degenerate in the highest order of the derivatives, then its Hamiltonian will be linear in one of the momenta. Because it's linear in one of the momenta, all of a sudden it's unbounded from below, and you have an Ostrogradsky instability, which in many but not all cases necessarily can be interpreted as a Gauss degree of freedom. Yeah, and because it's unbounded from below, blah, 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 blah. Yeah. Okay, very good. So I will now proceed to give you a simple demonstration of the Ostrogradski theorem and also an example. So let's see here. Oh, by the way, are there any questions? Okay, very good. So let's consider Lagrangian. Depending on one canonical coordinate q, its derivative q dot, and then q double dot. Okay. So you can easily show by variation that the Euler-Lagrange equations for this guy will be of the form dl dq minus d dt dl dq dot plus d squared dt squared dl dq double dot equals 0. Okay? Now, what we can do is we can define q1 as q and capital Q2 as q dot, right? And we can introduce a Lagrange multiplier, lambda, for Q2 equals Q1 dot. Okay, so then this allows us to express an equivalent Lagrangian as L of Q1, Q1 dot, Q2 dot, plus our constraint. Okay. Very good. Then, if we, okay, wait. So this, okay. So then the Euler-Lagrange equations for this system will essentially be Q1 is going to get, let's see, L Q1 minus ddt dl Q1 dot plus minus Q lambda dt 0, right? Okay. Q2, then we have I will just do this. Minus lambda minus ddt. Okay. What equals 0? Okay, so immediately we can see that lambda is minus this. Derivative, right? And then finally, for lambda, we get our constraint, Q2 equals Q1 dot. Okay, so first step. Now, let's go over to the Hamiltonian formalism. We define the canonical momenta as the L bar, the Q1 dot. Okay, but this is just the L the Q1 dot plus lambda. if I am not mistaken. Yes. Right, which, okay, if we impose the constraint, will be the L dq2 minus d dt. If we also use the on-shell conditions here, dq2 dot. Okay. Okay, and then P2, dl dq2 dot, which is just, okay, yeah, that's just bar dl dq2 dot. Okay, we assumed non-degeneracy in the Lagrangian, so we can invert this. Specifically, we can invert this equation. So we can express q2 dot as some function of, well, in this case, on shell, it would be q1, q2, and p2. p1 doesn't enter here because essentially we've imposed our constraint. We're working on shell. Okay, now maybe I can just move this guy up for a second. Okay. Can you see? Okay, very good. Yeah, so now, basically, we can define our Hamiltonian. So the Hamiltonian will, of course, be P1, Q1 dot, plus P2, Q2 dot, minus this L bar. But if we work on shell, then just, yeah, this, right? Of Q1, Q1 dot equals Q2, and Q2 dot of Q1, Q2, P2. Okay, but immediately, right, we see that this guy, if we impose the constraint, is just Q2, right? And this is our function f, which depends on the canonical coordinates that we have up there. And as we can see, we have a term here which is linear in the momentum P1. And this essentially unbounds this Hamiltonian from below and in general introduces instabilities. Now, depending on the Lagrangian you have at hand, I think there are a lot of exceptions to be made, but this is the toy model that generally is used to show Ostrogradsky's theorem. Okay, now, I'm not done with the blackboard yet. I will show you an example applying all of this, right? It's going to be very quick, and then we'll move on with life. So let's do this. Okay, very good. Very good, very good, very good. So now consider that the Lagrangian of Q dot, Q double dot is of this form. Q double dot squared over 2 plus sigma Q dot squared over 2 minus Q squared over 2. Okay, so looks very familiar. So then, as we did down here, we're going to define Q1 as Q, Q2 as Q dot. And this will give us the canonical momenta. P2 equals Q2 dot, which implies that f of Q1, Q2, P2 is equal to P2. And we don't really care about P1. It's just a canonical coordinate at this level. We could explicitly compute it, but we don't need it when we go over to the Hamiltonian formalism. Okay, so then our Hamiltonian would be something like this. P1 Q2, right, plus, let's see, P2 squared over 2 minus sigma Q2 squared over 2 plus Q1 squared over 2. Okay, these two are sort of begging to be combined. Okay, we can do this. Rewriting. Right? We will get that this is equal to minus sigma over 2, P1 minus Q2 over sigma squared plus P1 squared over 2 sigma plus P2 squared squared over 2 plus Q1 squared over 2. And now you can see, so there is a canonical transformation you can make to make this even more explicit, but I'm not going to do it. Essentially, you can see that if sigma is 1, then this guy is ghostly. This guy is normal. These guys are normal. If sigma is minus 1, this guy becomes normal. This guy becomes ghostly. And you can sort of see how this higher derivative degree of freedom in the Lagrangian initially translates to a sort of ghostly degree of freedom in the Hamiltonian formalism. And that's all I have to say about the Ostrogradski theorem. So let's... Okay. Are there any questions? Okay, very good. Very good, that means I'm doing great. Okay, so, yeah, that's also one thing you could look up actually. There are many special cases, and there is a very well-studied model of higher derivative to ghost system. It's called the Pace-Uhlenbeck model, and it seems to be very important in understanding the ghosts that emerge in modified gravity. Okay. Yeah, okay. Very good. What? Globally stable ghosts. So, up until now, basically what I've said is, in theoretical physics, we have many times these degrees of freedom that show up that make our systems potentially unstable, right? And generally that is the case. And for a long time, people thought that this is actually, this is always going to be true. Ostrogradsky's theorem, et cetera, but recent work has found that actually, no. There exists quite a wide class of systems where you can have a ghostly degree of freedom and retain actually global stability in all of phase space, meaning you can pick any initial parameters, evolve your system in time, and you will have bounded motion in phase space, essentially. So you won't have any runaways. Okay, so this work was mainly done on classical mechanical systems. For field theories, I will get to that in a second. Yes, that I already said. Yeah, so these two papers, please read them. They're actually very nice. They discuss this, where the second one actually gives an analytical proof to boundedness of motion for these sorts of systems. So I would check them out if you want. God, the range on this is not amazing. Okay, so the basic idea of these systems then is that you start from a very specific class of integrable systems where you have, at least at quadratic order, you have just decoupled harmonic oscillators, and they interact quite non-trivially through this sort of interaction term potential right there. And the idea is that you ghostify these systems. Now, how does that work? Well, there is a complex canonical transformation you can consider, something like this, which essentially will turn squared momenta terms to minus squared momenta and squared positional terms to minus squared position. Essentially, this is going to unbound your Hamiltonian. Now, if you also ghostify your initial conditions, it's an equivalent system. But if you only ghostify the Hamiltonian and then you use real initial conditions, you have a completely different system. The benefit of this is that these systems are integrable, which is essential for the boundedness of motion in these systems. And the integrability remains under the canonical transformation. And that's sort of the foundation of this result, is that if you have an integrable system with a ghost in it, you can sort of relax a bit. Yeah. And they provide analytical proof, very good, no runaways. So, what about field theory? Because this is classical mechanics. Now, field theory is a bit more complicated. There's very, very recent work, just like 2 weeks ago, where the same guys who worked on the classical model have investigated 1 + 1 dimensional classical field theories containing ghosts. And basically the arguments that they make are that, okay, you can have either benign ghost fields in the sense that they do run away. You will always have a runaway, especially field theories, but the runaway is slow. And it's so slow that it actually takes infinitely long time for the runaway to become problematic, which means, okay, maybe we can live with it for a while, in a sense. They also discuss how you can sort of slow down the instability by either giving the field a very large mass or a very large frequency, or introducing self-interactions that compensate for the spurious excitations of positive and negative energy modes. This is not analytical, though. They only have numerical simulations that are sort of rescalable, in the sense that they've done simulations that they can rescale, and you can sort of see that it suggests stability for the models that they consider. Why do I bring up all of this, both the classical mechanical case and the field theoretical case? It's because, well, we have this Ostrogradsky's theorem, right, which tells us that, okay, you're generally going to see instabilities from higher derivatives. Okay, the Hamiltonian is unbounded from below. Generally, you will see runaways. But there are exceptions, and there are actually a lot of exceptions, and that's the point. It's that we actually don't know a lot. We know a lot, but there is a lot to learn about ghosts and their stability, and generally about the dynamics of Lagrangian and Hamiltonian mechanics. Okay, so now let's move on to my work, which is on the quantization of such a model. So the classical model that I have considered is this guy, right? So you can see that we have at quadratic order, we have a harmonic oscillator in the x direction, one in the y direction, but the one in the y direction is ghostified. The interaction potential looks something like this. It's very non-trivial. And these are our coupling parameters. They're positive. So you can see that this is a 6th order polynomial, and it's actually not decouplable. Like, you cannot find a canonical transformation to decouple these 2 degrees of freedom. They are interacting. Okay, I said that this system is integrable, which means it has an integral of motion, that is, a conserved quantity. This integral of motion is given by this guy, and you can see that it is also at quadratic order 2 decoupled harmonic oscillators, but now it's not ghostified. Okay? Furthermore, wait, I can't even see the... Very good. Furthermore, this is the interaction potential, and you can show that this guy is positive definite. Okay? It's positive definite, which means it has a finite volume in phase space, and because it's conserved, right, you will have bounded motion from this system. Okay, now, I'm going to show you some plots. So this is the potential, right? This is the interaction potential that you guys just saw. And we can see that, yeah, oh, wait. Okay, let me go back. No. One moment. Okay, very good. Very good. We can see that this is a sort of saddle potential, right? Decreases down to infinity in the, along the x-axis and up to infinity along the y-axis. This is a weak coupling, strong coupling. You can't really see a big difference, but it's there. And this is how it looks in the strong coupling in a 3D plot. Right, okay, this is the Hamiltonian. The integral of motion, on the other hand, looks something like this. In the weak coupling, this resembles a harmonic oscillator. And then in the strong coupling, you can see that we get this sort of pillow shape of the potential, right? It's squaring off. And it starts actually growing very rapidly because it's a sixth-order polynomial. This becomes relevant because if we quantize this, right, our wave functions should sort of inherit this shape in a sense. So that's a good qualitative test. Yeah, this is a 3D plot. I couldn't really figure out how to make it pretty, so. Okay, okay, very good. Very good, so now, how do we quantize such a system? Now, there are different ways of going about it. I know that there are, even before these kinds of systems, I earlier mentioned this Pays-Uhlenbeck system, which contains ghosts as a higher derivative theory. People have considered different ways of quantizing ghostly systems to circumvent the sort of vacuum instabilities that arise because of the Hamiltonian being unbounded from below. So PT symmetric quantization, Weyl quantization, which is more geometric, and you define basically how your Poisson bracket quantizes. We simply just did the canonical quantization, just straight up what you learned in your first quantum mechanics course, and it seemed to work out quite well. So we go over to operators. These are our commutation relations, and yeah, our operators are going to look just basically the same. There's nothing different here. One thing I forgot to mention, the integral of motion contains this term, which sort of mixes position and momentum. I'm not going to comment so much on that. Okay, so now we've quantized this Hamiltonian. The next question is, what do we do, right? Because the Hamiltonian is unbounded from below, right? So what's the vacuum state? Is there a vacuum state? What about the spectrum? Is it going to be discrete? Is it going to be dense? Is it going to be continuous? Are we going to have degeneracies? And how would we, in that case, predict them, et cetera, et cetera? There are a lot of very interesting questions you can ask, and many of them are very difficult to answer. But there is a key point here. Okay, wait, before I get to that point, yes. I don't have the expression here, but generally, Hamiltonians in quantum mechanics are elliptic, right? Ours is not. Ours is sort of, well, non-elliptic. Let's just call it non-elliptic. How does this affect the Schrodinger equation? We don't really know, right? What about time evolution? What about stationary? We don't really know. But, and this is a very important point, remember the integral of motion. Classically, it means it's conserved. It commutes with the Hamiltonian. Does it still do so in the quantum case? Yes, it does. Right. And what do we remember from linear algebra about commuting operators? They share eigenvectors, right? And we know that this guy, I'm going to mention it in a bit, this guy is elliptic and it's positive definite. So we know how to treat it in quantum mechanics. So we can just use this guy to define the spectrum. Yeah, we can do that. Okay, and here's another point. We can actually define a new integral of motion that's dependent on the Hamiltonian and the positive one as so. This is also going to be positive definite and elliptic. And so both of them are going to have discrete spectra. They're confining. But they have different frequencies and masses, so we can decompose the Hamiltonian as such. And then what this means is essentially all of these have common eigenvectors. So if you want to determine the eigenstate or eigenvalue of the Hamiltonian, you can just take 2 times the eigenvalue of H plus minus the eigenvalue of H minus. And this way you can sort of try to analyze the structure of the spectrum. We're doing that right now, so we're not really done with it yet. We can get some insight on this, essentially. Okay. Now we get to the numerics. So we solved this system, not analytically because it's highly non-trivial, but we did so numerically to get some insight on how the wave functions worked, et cetera, et cetera. So in the time-independent case, I used a pseudospectral method. So you could read this book if you want to learn more about that. I think Ledvinka would be happy to see this. This allows us to determine the lower level eigenstates, and it allows us to test perturbation theory, standard perturbation theory. In the time-dependent case, I used this sort of split operator method, which is unitary and preserves the norm. Let's keep it at that. This allows us to check whether our eigenstates are actually eigenstates. If we have vacuum decay, as I mentioned, because the Hamiltonian is unbounded from below, you might have, energy just disappearing, right, or probability. So we can check this, and we can assess the dynamical behavior of the system. Does it behave normally, in a sense, Okay, so these are the first 4 eigenstates in the strong coupling limit, meaning our parameters, let me go back. It's so slow. Wait, maybe I can do this. Okay. I don't know if you remember, but in the strong coupling limit, right, the potential squared off, right? It became this sort of pillow-shaped potential. And we can see that reflect in the, can you guys see the, can you see the screen? Which one is it? Turn them off, just completely turn them off. I think that's better. Okay, very nice, because now you can see the gradients. You can clearly see that the shape of the potential has affected the shape of the wave function. So we have this ground state that looks like a squared off harmonic oscillator. Ground state, here you have the first excited state, second excited state, third excited state. And in the 3D plot versions look something like this. Very nice. Okay. Now, I'm going to show you an animation. And this is basically, I've taken the potential in the strong coupling regime, so it has this pillow shape, and I've just taken the ground state of the normal harmonic oscillator, and I've placed it in the middle. And on the right, I have the numerically computed ground state. And as expected, the numerically computed ground state is just completely unchanged. The harmonic oscillator one is going to, spread out and bounce back and forth, and it does so in this sort of squared off manner, which is exactly what we expect it to do. Now, here's an animation of essentially taking the ground state of a coherent state, which is also the ground state of the harmonic oscillator, displaced it a little bit in the x direction, and allowed it to oscillate back and forth. Classically, the oscillation period, this is in the weak coupling limit, so the potential is almost like a harmonic oscillator, but not really. There's a small difference. The idea is, nonetheless, that the classical oscillation period is about 2 pi. And so I've run it for about 4 or 5 periods. So we're going to see here, more like 6, actually, 6.5. Now, because the potential, you might ask, does this deviate too quickly from the classical path, et cetera, et cetera. Because the potential is growing so rapidly, so I actually displaced this guy by quite a lot, by 1.5 units. So I am not surprised by the fact that this guy starts, losing its shape, et cetera, after a few oscillations back and forth. But essentially, yeah, I would say it looks reasonable. Oh shit, my computer is dying. Holy shit, wait. One moment. Very good. Okay, and now basically I've taken the same Gaussian and I've placed it and I've said, look, just do your thing. Don't oscillate in one direction. Now, does this tell us anything concrete? No, not really. This is just a qualitative assessment. You know, it's a presentation. I wanted to show you some nice plots and animations. Essentially, yeah, this shows the dynamics of our system. It doesn't appear to be losing probability. We've made more formal tests. I just chose not to include them here. Essentially, what we did was we took the ground state, we placed it at the center, so it's just stationary, and then you pick one point on that, right? And you look at the real and the imaginary parts during time evolution for a very, very long time. If it is a ground state or an eigenstate overall, it shouldn't change in time, and time evolution should just amount to an introduction of a total phase, right? We can actually compute that phase because, well, we have the energy eigenvalue. So we can plot the exact sort of phase that you would get if it is an eigenstate, and then we can compare it with the numerically computed one, and they coincide. So I don't have that plot here, but essentially, yeah, things work. Okay, now, to summarize, what we've done so far, and we're working more on it, is we've canonically quantized a globally stable ghostly system, essentially a two-particle system that contains a ghost degree of freedom that is coupled to a physical degree of freedom through a very non-trivial interaction term. Why, how does it appear in nature? That's a different story. The point is, this system has an integral of motion, which first of all keeps the system stable, but it also allows us to get a notion of a spectrum and a ground state for the Hamiltonian, which essentially otherwise would be ambiguous. We have seen that perturbation theory seems to work. We've only looked at the ground state so far. There are a lot of questions one can ask here, because essentially you can perturb in the integral of motion or in the Hamiltonian, and depending on which operator you choose to do your perturbation theory in, you're going to get different corrections to the same background state. The question is, should and will these converge onto each other? Naively, yes. One would have to check this formally. We haven't done that yet. Nonetheless, perturbation theory seems to work, and numerically we've seen that the eigenstates look as if we expect them to do. Time evolution also appears to be healthy, although I haven't shown you some of the rigorous tests that we've done. There are still many interesting things to investigate here. So we've, well, numerically, but also perturbatively investigated the lower order states. Standard perturbation theory is not really going to work at higher energies, so then you need something like WKB, but that's really not trivial in 2D, so that's a different story. But generally, that would be very interesting to investigate, especially to consider the spectrum of the Hamiltonian. Because if you recall, maybe I can like hyper fly back to, yes, wait, okay, my computer froze. That's okay, I still have some time, so this is perfect. There's a break, you guys can, okay, let's see if I can go to the slide. Let's do this, let's mirror. I don't need the fancy effects anymore, so we can just do this. Okay. Yeah, so if you recall this decomposition that I told you about, essentially, because we're subtracting the states or the levels of H plus from, or H minus from H plus, there is a question of degeneracy here, right? You could have two completely distinct states in H plus become degenerate in H because the difference or the distance between the two levels in H plus and H minus would be the same, right? So that's one thing. And then another thing is, how do the states look around the vacuum? So the vacuum state for the Hamiltonian will be the vacuum of H plus minus the vacuum of H minus, right? The question now is, if we go to high energy states, what will happen to the energy levels? Are these going to converge onto each other in H plus and H minus? And are the, most important, are the distances between the two levels, between the two operators, going to converge to some constant value? Because that would imply that you will have infinite degeneracy in your ground state in the Hamiltonian, right? That's not immediately obvious. Or what could be the case is that you have this sort of gathering. So like you have H plus here, which has some levels like this, and then H minus, which has, I don't know, something like this. And in H then, what could happen for high energy states is that this is your vacuum, right? And then you have a dense collection of states above and below. This could technically happen. We don't really know yet. So this is something to investigate, and we think that the key in it is trying to look at how the higher order states can be perturbatively investigated with, I don't know, WKB or something similar in H plus and H minus to sort of deduce if, you know, what happens to the distance for large energies. Okay, that was a long point. Yes, okay, I think I've covered everything here. So then, basically, I would like to summarize what I've talked about today. So, as I mentioned at the beginning, ghosts are very relevant in theoretical physics today. They do appear, whether we like it or not, in modified gravity theories, and they do so, or we work with modified gravity theories because we have to. Furthermore, there have been suggestions, at least in the field of cosmology now, by observations, that we might need ghosts to explain the accelerated expansion of the universe. So they are relevant, and thus it's also very relevant for us to gain some insight into how they behave dynamically, both classically, classical mechanically, field theories, and then quantum, of course. Ghosts are problematic at face value, as I have presented you with the Ostergradsky theorem, with the example that we looked at. But nonetheless, there exist stable systems, and that I've also showed you. So, to summarize, I would say there seems to be a lot to learn about ghosts today. We don't know everything there is to know about them to say whether they're good or bad. We can only characterize them from a situation-to-situation basis. So that's one point. And then my final point is this also implies that there's a lot to learn about Lagrangian and Hamiltonian mechanics in general. We do know a lot about it, don't get me wrong, but just because the physically viable theories that we have now look a certain way doesn't mean that they always have to, right? And with that, with my little philosophical tangent there, I would like to summarize and just say thank you. Thank you for listening. Are there any questions? Yep.
Yeah, so, well, it sort of seems that your ability to analyze the spectrum after the quantization hinges quite heavily on the fact that you've been able to identify not only one integral of motion, but also the other one, the H minus, right? So does this sort of method, you know, like identifying several integrals of motion in order to decompose the overall Hamiltonian work in general, or?
Good question.
A specification of this program?
I guess, yeah. I would say it depends on your system, right? Depends on your system. And in our case, you can express it as a difference. I think that's an important point. So the point here is that the Hamiltonian is unbounded from below. It's not confining. So it's not immediately obvious that you will have a discrete spectrum, right? But if you do have a normal Hamiltonian, like a usual one that's bounded from below, first of all, your vacuum is going to be unique. But secondly, you will have a discrete spectrum, unless if it's like, okay, you know, you have some continuous part of the spectrum. So in those cases, I don't know if it would help that much to make a decomposition. Maybe if you do have, let's say, if you do have an integral of motion, maybe you could decompose the Hamiltonian into a sum of that and something else, and then you could look at the sum of those spectra, absolutely. Yeah, in this case, it was a little bit useful to sort of gain at least some intuition on how the spectrum might be constructed, because it could be, like if you explicitly compute the spectrum, okay, so if you numerically try to solve the Hamiltonian, just straight up the Hamiltonian with the pseudospectral method, the ordering of your states is going to be a bit ambiguous. Right? There's no clear direction, because you're not going to get solutions that go from minus to plus. You're going to get like minus, plus, minus, plus, minus, plus. So you don't have a sense of ordering of your spectrum, but you do for the integral of motion. So that way we can order our eigenvectors, right? And then we can use that to order the spectrum of the Hamiltonian, the energy levels of the Hamiltonian. And essentially, because both of them are discrete, well, immediately you'll see that if you don't have obvious degeneracies, then your spectrum in the Hamiltonian will be discrete as well, naively, at face value. But this also gives us some insight into how you could have degeneracies, or how you could have this sort of, you know, gathering and condensing of energy levels around the vacuum, essentially, or any other state. I don't know if that answered your question. Any other questions?
I have a question.
Yeah, go ahead.
So the Hamiltonian is very special, right? It has 6-order polynomial coupling.
This one?
Yeah.
Yeah.
So why this one?
Oh, this is just one of several. Like there is an entire, so basically I didn't write it out because it's actually quite messy. But essentially there's an entire class of Hamiltonians. So look up this paper here. Essentially, here, the second one, global and local stability for ghost, ... at archive. That one presents several classes of ghostified Hamiltonians with integrals of motion, right? So, of course, they are also very specific. You have to demand some properties of the potential and of the kinetic terms, but this is just one specific example of that general classical theory, class of classical theories that we've chosen to quantize to just naively get an understanding of, okay, this seems to be bounded and stable and working nicely in classical mechanics. What about quantum? Right? Because quantum is a statistical extension of classical mechanics, I would say. Did that answer your question? Very good. Anyone else? Okay. Thank you.